All right. First of all, thank you very much for the organizers for inviting me and letting me be part of the celebration. And thank you to Dan for being born and also giving us reason to be here, and for the years of very diverse and very inspirational mathematics, and also your mentorship. Thank you. So I'm going to talk about finite groups. And as I'm going to talk about finite groups, I'll start with characters. So the first set of characters are the people involved. This is joint work with Benson, Iyengar and H Krause. And there is also related work from a somewhat different perspective by Krause. Okay, and the other set of characters are the categories I'd like to study. I was told that the mouse might work. Okay, I'm interested in representations of a finite group. K is going to be a field of positive characteristic, and I'll assume that we're in the modular case, meaning that the characteristic divides the order of G. And then the category we study is representation category of G, or modules for its group algebra. Now, we have here are the real characters that will be playing their special roles. So the category of the bounded direct category of modules over PG, then the category of the bounded direct category of projective modules, and then I can take the localization of this one with respect to projective modules and get the stable category. And then at the top, I have the categories of big objects, whereas the bottom line are going to be small objects, and I'll make this more precise. Now, these things have other names. The stable category, actually, the way I put it here, by definition, is the singularity category of G. If you think of the analog with algebraic geometry, then the singularity category is precisely that localization. And the one in the middle, we can also think as the category of perfect complexes on the classifying stack of G. These are just names. Then the fact that the stable category is the one that appeared several times yesterday already is a theorem due to Buchwald's and Rickard independently. And so we can think of it, and I will think of it as just representation category of G, and then we factor out maps that factor through projective or injective modules, which are the same in this case. So perhaps that this talk belongs to the set that you heard yesterday, but since it's been a little bit of time already, I am going to repeat some of the definitions, even though basically everything I need was already either defined or alerted to on Monday. Okay, so I'm going to start with a bunch of formalities. We're going to work with a symmetric, of type symmetric, tensor triangulated, shortened as TT, R linear category. I'll assume it has arbitrary sentence index co-products and that the co-products commute with tensor product. There are lots of other conditions which can appear, I think, mostly in Kant's talk, which are also being assumed. One will be the tensor unit, and we also have the suspension functor, sigma, on T. So I'm going to work with three main examples, and then I'll try to argue that these are actually two examples a little bit later. So the first is the category KH. So this is the big category, or the eighth category, if you want, that corresponds to the main category I'm interested in, the derived category of modules of G. Then the stable category, which is another main category I want to study, and it's the big stable category of G. But also we'll look at the example that comes from commutative rings, the derived category of modules for a commutative, usually Noetherian ring. Okay, so other formalities. T, by some Brown representability nonsense, has an internal home. This is what Paul denoted with square brackets yesterday. I'm going to use the curly home for that. It satisfies the usual injection isomorphism. And then we'll define the compact objects in T as the ones which commute, homes from which commute with arbitrary coproducts. And then the dualizable objects are the ones for which, if you take the internal dual and tensor and map into the internal home, that's an item. So Paul actually did most of the motivation for me very nicely yesterday. And then these are two different ways of looking at like small objects at in the category T. And sometimes these are different ways, even though for many examples you often think of, they turn out to be the same. Yeah. Okay, more formalities. So we will say that subcategories think if it's full triangulated and closed under taking direct sums. Localizing if same thing, closed under direct sums, arbitrary coproducts. And it's a localizing tensor ideal if we can also tensor with arbitrary objects in T. And then I'll use notation thick and log for the corresponding minimal thick or minimal localizing subcategories generated by family of objects in the matrix. Okay, I think at least for now, this is going to be the last slide with definitions. T is compactly generated if we take compact objects and then take the minimal localizing subcategory and we recover T. And it's rigidly compactly generated. It's compactly generated and compact and dualizable or rigid objects are the same. And we have a lot of examples where this happens. Particular in my three main examples, for the category, homotopy category of injectives, I probably should have said what it was. So this category T, just the homotopy category of complexes of injective KG matrix. You take the compact objects and you get the bounded direct category. For the big stable category, the compact objects give small stable category. And for the direct category of commutative ring, you get the bounded direct category of projective matrix. If one goes back to my sequences, basically all I'm saying is we take the top thing of big categories and we take compact objects and we get the bottom thing. Okay, one other thing that was playing a role, my category T was R linear. This means that they have a graded commutative ring which acts on T. And for the purposes of this talk, I will mostly consider, probably only consider what's called a canonical action, the action by which is given by sending R to the graded endomorphism ring of the identity of the category. So again, that was already defined, probably more than once, but anyway, the endomorphism ring is just the direct sum of all com sets into the shifted object. We can do it both for one and then for any two objects X and Y. And then the action is just given by the tensor structure on our category. So you have a map, well, just written up there. One map, another map, and you tensor them together. So the endomorphism ring of one naturally acts on home spaces of my category. And when I say that it acts on the category, this is precisely what I mean. And then by having any homomorphism from the ring, graded commutative ring, into the endomorphism ring, I get the action of such. Sigma. Sigma n was the shift of the suspension in the triangulated category. Questions, by the way, are most welcome. Okay, so these are familiar objects in the examples that I'm looking at. So if we start with a finite group, and the homotopy category of injectives, the endomorphism ring of the identity, it's just the extensions of the trivial module. The identity is the trivial module, and we just get back the cohomology of G. For the stable category, you get state cohomology. But in terms of the actions, I'm going to look at the map of the usual cohomology ring into the state cohomology ring and act by the usual cohomology. The usual cohomology ring has this advantage that it's a finitely generated object. And for the direct category of commutative ring, I just get that commutative ring back. And there the unit is A itself. Okay, so getting back to what I actually want to do, I want to study this category fiber-wise. So in a way, what we've done is we have this ring R, which is usually the endomorphism ring of one, and it acts on the category via acting on home spaces. So, and it's a commutative ring. So I can bring in various things we can do in commutative algebra and use them, but for my categories. So in particular, I want to look at included fiber categories at the prime P, just as we can localize at the prime P, or we can take specializations to prime P, I'll do it in the category. So, start with my ritually compactly generated R linearity category. I think I have finally explained all the names attached to that category. We fix a homogeneous prime ideal. All my ideals are going to be homogeneous. Okay, so we say that an object is P-local if on the level of home spaces, it's P-local. So for any compact object in my category, I have an isomorphism between the localization of the home space and the original home space. And we say that it's P-torsion if, again, the home spaces are P-torsion, namely, if I take any ideal which is not in the closure of P, in the Zariski closure of P, so it doesn't contain P, and localize, I get 0. So basically, I only allow P-torsion in there. Okay, so by doing this, I can pass from my category T first to the localization of this category, and then to the category of P-local and P-torsion objects. So this is the category which I'll call gamma P T. All P-local P-torsion objects in T, and some Brown representability nonsense, which is quite involved, and which actually was basically described in Ken's talk yesterday, almost. You just had to do it twice for 2 different things. You can construct gamma P as a functor. It's an exact tensor functor from T to T. So the image is this subcategory of P-local P-torsion objects. A picture to have in mind, which is not precise, but kind of suggestive, is what we're trying to do. If we just take a module of a ring, we localize it, and then we kill the P part. So these are the 2 stages we're trying to reproduce, except that we're doing it on the derived level. Okay, so this is the fiber category. Yes. Another thing I want to have in the vocabulary is the support that one can define using this gamma P functor. Again, it's the ring R is underlined here. So everything happens with respect to the action of the ring R, which is the endomorphism ring, the homology ring for me. But still, everything that happens depends on the geometry R, properties of R. So we define the support by just taking all prime ideals in the spectrum, homogeneous spectrum, such that the functor gamma Px doesn't vanish. So if we specialize to the commutative algebra case, then we get the usual support when you take a complex and you take a derived tensor product with the relative field, and you check whether this is true. So another way to think about this fiber category, then, is these are all objects which are supported precisely at the point P. So by doing this, like localization and the P-torsion, we isolate the part which is supported at the point P. This guy also has other stage names. This is Grothendieck local homology, if you're coming from the commutative algebra perspective, or the record idempotence. And this name did, again, appear yesterday several times. And they were first constructed by Rickert in the representation theory. Okay, now I want to quickly argue that even though I keep listing 3 different examples, at least if I'm interested in these fiber categories, I basically only have 2 examples. Because when I take fibers of the homotopy category of injectives or the stable category, I more or less get the same thing. So the precise statement is, we take R to be the homology ring. If you take, it's called the irrelevant ideal, so take all positive degree homology elements, need maximal ideal we have in that homogeneous ring, and localize the homotopy category of injectives, we get the direct category. But then if you localize it any other P, smaller one, you kill this guy, and this gamma fiber categories are the same, whether you do it on the k-inch level or the stable level. So basically, once we want to study the fiber category at a non-irrelevant prime ideal, then we can either look at the stable category or the k-inch category, and there should be no difference. And I'm going to go back and forth between them, not thinking about it. Okay. So one indication that these things are important is given by theorem of Benson, Iyengar, and Krause from 2008, who produced a stratification of the big stable category via this gamma p functors. And one way to state it is that the fiber categories gamma p give you all minimal localizing tensor ideals. And so you cannot find anything smaller than those. So if you want to study a category using like the minimal possible localizing ideals, here they are. They're all described by, they're classified by the primes in the spectrum. And there's a parallel result by Niemann for commutative frames, which basically tells you the same thing for direct category of commutative. Okay, so I want to study this category gamma PT. It's a compactly generated tensor triangulated category, but it has some peculiarities. One way we try to study categories sometimes when they're compactly generated is you want to take the compact objects and then see how much you get from there. If you take compact objects of this category, again, as was pointed out by Paul yesterday, you don't even get the identity in there. So the identity in this fiber category is just gamma p1. You apply the function to 1, but it's not compact. On the other hand, it's dualizable. So if you look at the category, subcategory of all dualizable objects, let me be denoted by D, gamma p Td, then this category is bigger than the compacts. It still kind of consists of small, in this different sense, objects, and it does contain 1. Again, my bidding was done yesterday. I'm trying to argue that this is a reasonable, interesting, reasonable category to study. So it contains record idempotence, but it's nice enough compared to the entire fiber category, big fiber category, gamma PT, which has all sorts of weird things happen there, which don't happen here. One of the results, which I might have time to state in the end, is that this category of dualizable objects turned out to be a Krause-Schmidt category, which is not true about the entire big category. Okay, so we set out to see what we can say about it, whether we can describe it explicitly, and what is it? Should probably say this was a long-term project. It's been going on for a while. And then in the fall of 2022, in Bonn, during the tensor triangular trimester there, we discovered that John Carson was thinking about similar things from a somewhat different perspective. And then John, being a team of one very efficient and very organized person, posted both of his papers in 2022, and I think they appeared by now. Our preprint just showed up on the archive about 3 weeks ago. And then, of course, as usual in this business and stable homotopy theory, they did look at these questions a while ago and came up with various things, which I'll mention in a few slides. Okay, so what can we say about this category? One thing we can say is that it has the action of a completed cohomology ring. And turned out that this is a corollary of our studies of the duality properties for this fiber category. So a number of years ago, we showed that this category is what we call Kornstein, and it satisfies third duality. And then the calculation of the endomorphism ring of 1 is a direct consequence of that. So again, 1 in this category, this is somewhat misleading, because now we're looking at the fiber category, and 1 here is gamma P1. You take the trivial module, and then you apply gamma P to that. It's going to be some big representation, usually. The endomorphism ring is just the X of the big module, and this is the cohomology ring completed at P. So in particular, it acts on my category. So here's where conclusions actually show up.
I have a quick question.
Sure.
Is the result that a certain ring here is Lorenstein and therefore you just like use local duality to get this?
No.
Okay.
So as we'll see later on, we actually define what it means to be Bornstein,
Oh, okay.
and then we prove the category is Bornstein. But you take the Grothendieck definition of Bornstein. Basically, you show that one it's an isomorphism of modules on the level of on the level of derived categories. Okay, so we have this R-hat linearity going for us. Another thing that one can say, more or less immediate, is so we take the identity, it's a dualizable object. So it certainly sits inside there. And then we close under all the operations we have. So we take the thick subcategory generated by the identity, it also sits in there. In fact, if you take the thick subcategory generated by gamma P applied to all compact objects in T, which in the representation theory case, just finite dimensional modules, then we get dualizable objects. So as Paul actually, in one of his papers, it takes the norms of Steele not to conjecture that these things are the same. And they turn out to be the same. I mean, the norms of Steele conjecture refers to different. But anyway, so we're trying to prove that they're the same and they're the same. And here's the main theorem. I'm going to state the theorem, and then I'll spend a few slides explaining what the theorem says. But the theorem is for a stable category or the homotopy category of conjective of a finite group G. We take a prime, which is a homogeneous prime, not the irrelevant ideal, so it's in the proj. We also fix a pi point, I'll get back to that, which corresponds to this prime P. And then the following things are equivalent. So first of all, dualizable objects and the thick subcategory generated by the unit, not by the unit, by the compact object. Okay, I also fix the compact generator for G, and here I can just take the sum of all single modules. So the thick subcategory generated by gamma PC and the dualizable objects are the same. So this was the conjecture of gas from the previous slide. But the way one proves it is that one interprets this condition in two other sort of more representation theoretic ways. And the first one is that M has finite length. And the other is that we can characterize it by taking a pullback of M with the extended scalars and checking whether that is finite dimension. So the plan for at least part of the rest of the talk is I'm going to explain what 3 says, and then I'll explain what 4 says. Quickly going back to stable homotopy category. So in that manuscript by Harvey and Strickland, they pointed out that going from thick of the compact generator, gamma PC, to the dualizable works in that context, and this is actually pretty general. Then going from dualizable to finite length is also pretty general, but the implication from 3 to 2 is not true in homotopy. Also, when I state the analog of this theorem, which actually appeared before representation theory theorem for the commutative algebra. So if T is the derived category of a commutative ring, and ask exactly the same question. And here, the third condition is you take a complex in gamma P D of A, you specialize it to a point P, and the rank of total cohomology of this should be finite. And here, switching the notation, the unit in this category is the usual local cohomology. why R gamma P is here. Okay, so going back to my 4 equivalent conditions, the third one says that M has to have finite lengths in that category. So once again, I have the action of R. So finite length is defined in terms of the action of my ring R and looking at the Holmes spaces. I'm going to give a whole bunch of definitions, but again, it's all along the same lines, on the same philosophy as how Holmes spaces behave with respect to the action of R as R modules. So we can define what it means to be Noetherian. Just Holmes spaces are Noetherian when you look at Holmes spaces from compact objects. What it means to be Artinian, and what it means to be a finite. All very natural things coming from cumulative algebra representation. But then in the case of the stable category of a finite group, one can characterize this property of finite lengths in various ways, depending on which category you want to work with. So finite lengths, basically by definition, means that if you look at the Holmes spaces in this fiber category from compact objects, then they have finite lengths as modules over the localization of R. Well, checking this requires knowing what compact objects are and taking Holmes in the fiber category. One can reformulate this by going back to the category T and checking that Holmes spaces are Artinian over the localized ring, where we only look at compact objects in T, and these are just finite dimensional modules. And I'm going to put this other condition here. So one can also, there's a duality, local duality category. I'm going to define what it is, but one can define local duality and do everything in terms of Noetherian properties, which in the order, but then you have to work with the completion. We can make one more comment why this paper took us so long to complete. So when the original draft, this paper appeared, it actually had, instead of 4 conditions, it had maybe 12 conditions, 13 equivalent conditions. And then it took about 1.5 years to cut it down to 4 conditions. But there are many, many, many others one can put. And in particular, one can express a lot of those things in terms of the completed category, like lambda P category instead of done. And this is just one sort of shadow of that. Okay, so to prove the theorem, as we already know from stable homotopy category perspective, we need to show that if you have an object of finite length, and one can choose whatever description suits you best, then it can be built from gamma PC, where C is the compact generator of T. Basically, this is what one has to show.
What is DP in that? Both lengths?
Right. So there is it's a local duality functor. There is a duality functor gamma P that one can define, and this is it. Thank you. Okay. So now to prove that building thing or the implication from finite lengths to being in the thick subcategory of gamma PC, we introduced the notion of local regularity, which is basically the notion of strong generation. I'm going to remind you what strongly generated means. So now again, we start with an arbitrary tensor triangulated category. Actually, I don't even need triangulated to start with. Sigma is the suspension, the shift. Then for any object X, instead of taking the thick envelope right away, I'm going to do it in stages. I'm going to try to keep track of like how many extensions I need when I'm building something out of X. So thick 1 is just going to be the additive closure of all the suspensions of X. Okay, so we take X, we take suspensions, we take direct sums, direct sums. Let's take 1. And then for each next step, I'm going to take a map from something in thick 1 and something in thick n-1, which I already constructed, and take the code. So I'm allowing like one more extension to get to thick n. If I continue this process indefinitely, I'll get the thick envelope of X. But I really want to know whether it stops at some point. And so we'll say that an object X is a strong generator if we get the entire category T by only doing this finitely many times. If it's thick N for some N. So I can build everything by only taking like N cones or N extensions of X. And then the category is strongly generated if it has a strong generator. And if it has a strong generator, then it's easy to show that any generator is a strong generator. So basically, rephrasing the same thing, strongly generated means that there's a global bound on how many extensions you have to take to get to the entire category. Okay, I'll also need a notion of an Noetherian category, which is basically the finite generation, like general finite generation condition, which again appeared in much more sophisticated reincarnations yesterday. We'll say that the category is Noetherian over R, and I still have R acting on my category. If any whole space between compact objects is Noetherian module over. And then an R linear triangulated category T is R locally regular if it's Noetherian, and if it meets a compact generator such that if I take the thick envelope of gamma PC for any P, it's strongly generated. So basically, I'm requiring the strong generation for these categories for which I want to prove something for all P. If R is so if my category is tensor triangulated, this definition doesn't require a tensor structure. My category is tensor triangulated, and I have the endomorphism of 1, then I can define the global version of locally regular, but taking R to be the endomorphism. Okay, the sanity check, we take a ring and take the derived category of a ring. It's locally regular if and only if the ring is regular. So we didn't invent anything new here. And basically, if one follows through with the definitions, then you have to check something at each P. And at each P, for strong generation, you're looking for like a global bound on your extensions, like on your projective resolutions. And this gives you that localization at every P has to have finite global dimension. Okay, then basically the proof of the theorem, of the main theorem, has 2 parts. First, we show that if you have such a locally regular category, then the implication from theta 2 works. And I think this was probably absorbed by stable homotopy theory people already. What we actually prove is that K-inch for a finite group is locally regular. And here I'm going into K-inch. It's intentional because in this definition, I wanted my category to be Noetherian. And this happens for K-inch, but it doesn't happen for the stable category. But as I tried to argue, if you actually want to look at the fiber categories, they're the same. So the theorem itself, I get for fiber categories of the stable category. But to imply this local irregular notion, I want to work with K-inch. Okay, so that gives me the implication from 3 to 2. And so the main statement is that K-inch is locally regular for a finite group. I can look up a couple of notes from the proof. The proof basically consists of 3 steps. And the first step is the general one. We said that if we have, doesn't have anything to do with TT categories. If you have a compactly generated Noetherian R linear category, and if you have a compact generator such that the endomorphism ring of the generator is regular, with finite global dimension, then the category is locally regular. Of course, this, as many people in this room probably know, very rarely happens for finite groups. Sometimes, like you can take elementary billion characteristic 2. But other than that, it doesn't happen. But we can reduce to this case by a couple of finite descent results. Turns out that this local regularity is a relatively robust property, and one can descend via finite extensions of categories for rings to get to the finite group. Okay, now there was this last property, last condition in my theorem when I chose 4 out of 12, and that had something to do with pi points. And at least to my taste, it's a very pleasant condition because it basically tells you that you have to take some module and check that it's finite dimensional modular projectives. This is precisely what the condition says. And I put both the theorem for the finite group and for the commutative ring on the same slide to indicate that what happens for the finite group is we're trying to look for an analog of this last condition in the commutative case. So what does it mean? How can we interpret that the rank is finite? So one way was to look at the finite the length as a module, and the other is this pi point interpretation. I'm going to quickly describe or remind you what it means. So there is this theorem that Eric Friedlander and I proved already quite a number of years ago, which says that if you start with any finite group scheme actually, and a prime in the branch, then you can always find a map, just as the one I use in the theorem, from truncated polynomial ring on one variable to my group algebra, which map is called pi point. And I have to extend scalars here, basically to the residue field of P, almost to that, such that if I take the corresponding map in cohomology, so this map of algebras induces the map in cohomology, I take the kernel, take the radical, or take the reduced ring here. So this thing is basically a polynomial ring on one variable. Then the kernel is my ideal P. So I get P back. I kind of realize every prime ideal with the map of algebras. Such a map is called a pi point. And then if I start with P and construct the corresponding pi point, we'll say that it represents the prime ideal. Then if I have a map of algebras like this, I have the corresponding restriction functor on representations, except that I have to go from the stable category of G, have to extend scalars to my field K. Then I have the restriction functor. And so this restriction functor is precisely what this last condition says. And the theorem, which actually does apply to any finite group scheme, tells me that the finite length condition is equivalent to taking my prime ideal, taking the corresponding pi point, pulling back the module, extending scalars, pulling back the module, and just checking if that module is finite dimensional. Modular projective symmetry. I think this does appear in, so John figured that out. One corollary of this, which is always the question in this business, if you look at the construction of a pi point, there's no reason that for a given prime ideal, you just construct a unique map, and it's not true at all. You can have many different maps. And somehow it's not obvious that when you pull back by these different maps, then this condition is always satisfied. But this follows from this theorem because the first condition does not depend on the representative. So it doesn't matter which pi point you choose. Okay. Applications. I think John asked in, he certainly asked us is in Bonn. So you have this category of small objects. Now you can ask what its Balmer spectrum is. And Balmer spectrum is the spectrum of the completed cohomology ring. So in a way, it's again an expected answer to the answer that it's the endomorphism ring, spectrum of the endomorphism ring of the identity. I think it's not part of the conjecture that Milan stated, because we don't start with a finite tensor category, but it's very much in the spirit of it. So it's one of those examples that we're going to expect what the answer is. The question was how to prove it. We did, I think last week. So this is something that would be called a preliminary report in AMS meeting, but we claim that the spectrum is the spec of cohomology of the completed polynomial. And then for another sort of a long-winded corollary of what we did is that this category is a Krause-Schmidt category, which again is not true at all for the fiber category itself. I think Dave has a lot of favorite examples of how things go very wrong for the fiber category, and how you can decompose the same thing in many different ways. So here it doesn't happen. It's a very nice category. Okay, so I have three more things to say. So first of all, happy birthday, Dan. I was trying to find pictures of Dan in my own archives, and somehow it turned out to be very difficult. And I vividly remember taking some pictures I couldn't find. I did find one that's it's a very nice body sample set picture, but I think it was the best one that I had. This picture was taken also almost exactly 20 years ago, just as the one we saw in G's talk. Some people might recognize where it was taken, and it was taken during another 60th birthday conference. Wanted to seize this opportunity to mention that we are going to have a third rerun of that event in Los Angeles in August. We'll celebrate 80th birthday of Eric Friedlander, and everyone is welcome to come. Now I'm done.
Questions? So how much of your work do you expect to extend finite groups?
That's a very good question. I think you might have different divergent views on that. So, and this relates to a question I asked you a couple of weeks ago. So part of the proof is that you reduce to the case when you have finite global dimension for the cohomology ring. So one can ask, at least for the barrels for classical Lie algebras, whether it's true, and try to get it from there. We have various ideas, but we don't have either a proof or even a statement at this point, particularly because, at least for me, the fact that finite groups are locally regular so far is kind of deeply rooted in Coulomb stratification. This is what the proof does. The cohomology is very close, like kind of finite. It's trying to be local, but it's trying to be regular by being reduced to elementary abelian subgroups. Of course, it's highly non-smooth, but it's non-smooth in this kind of very fine ways. And for Lie algebras, it's very different. So I can't answer your question.
So what about the reciprocal? Can we hear the question?
He asked about the super algebras. Julia was going to explain exactly how it goes.
Maybe referring to Verostock.
Fair enough.
Other questions? This condition about stably finite dimensional. So the analog of that in commutative algebra is the rank of the module, the rank of the cohomology at every prime. Something like that.
Yeah.
Right. So if the rank is that rank, so do you expect this finite? You said that it is independent of the pi point you choose. Is it known that the dimension is the same, regardless of the pi point, like, or is it just finite? Like you just know that it's finite dimension, but it should be the same.
Very good question. I think now I don't even know it's the same. So it would be
Fine, so the question.
So basically you would be looking so at combs from like a point module, and that will depend on, so I think the answer is no.
So how do you think about this? Like what is this? What is the stable finite dimension attached to a Python? How do you, what is?
It's a compact object in there. So if we're happy thinking about when the object is compact, then it's a compact object in this table category. It's precisely the same thing. Maybe I should have said it that time.
Other questions? All right, so then, thank you again.